First, a bit about the IGS North American chapter. Our mission is to provide leadership in advancing geosynthetics, education, and research to attain their appropriate and widespread use as engineering materials. The leadership within this nonprofit organization are volunteers. We could not provide this content to you without the support of our members. Today, we welcome Dr. McGuire, who is an associate professor and head of the Department of Civil and Environmental Engineering at Lafayette College in Eastern Pennsylvania. Dr. McGuire earned his master's degree and PhD from Virginia Tech, working under the guidance of Dr. George Fields. Dr. McGuire previously worked for Schnabel Engineering and has been providing independent consulting services since 2008. Notable public sector clients of his include the U.S. Army Corps of Engineers, NASA, and the Naval Facilities Engineering Systems Command, also known as NAVFAC. Dr. McGuire and various co-authors have produced several practical design manuals for public and private sector clients, such as the manual for the U.S. Army Corps of Engineers, presenting an L-pile-based method to evaluate bending moments in batter piles, supporting flood walls in New Orleans. Dr. McGuire's research activities are focused in the areas of column-supported embankments, slope stability, shear strength characterization, and practical applications of remote sensing. Dr. McGuire has been a member of the editorial board for Geostrata since 2014 and a reviewer of multiple journals, including ASC's Journal of Geotechnical and Geoenvironmental Engineering. We also are joined by Elise Hummel today. She is part of the civil engineering class of 2022 at Lafayette College and has been working on the GGB3 model since August. Her work this spring is being supported by the GeoInstitute Geosynthetics Committee. At Lafayette, Elise is a superstar in and out of the classroom, leading their renowned steel bridge team, club rugby team, and the competing on the D1 fencing team. Elise interned with Keller last summer and has applied to graduate schools to study geotechnical engineering next fall. Prior to starting the webinar, we have a little housekeeping to address. We're only able to address questions submitted in the Q&A box on the Zoom screen. Do not submit questions or use the chat function during the presentation. Questions are being monitored by myself and our presenters and will be addressed as they come in. Continuing education certificates are available to IGS North American members and will be emailed directly to those that attend within a week from today. On behalf of IGS North America and our 100+ attendees, we welcome Professor McGuire and Ms. Hummel. The floor is yours.
All right. Thank you very much, John. Before I begin, John, is the screen sharing working okay and my audio is okay? All right.
From my perspective, everything is working perfectly.
Super. All right. Well, thank you all for being here this afternoon. Elise and I are very excited to talk about column-supported embankments this afternoon, and particularly a new design tool that we're working on and hope to have available to practitioners sometime this year. Special thanks to John Allen and IGS North America for giving us this opportunity today, and we're really looking forward to the webinar. Before I get going, I'd like to acknowledge a few folks, in addition to Elise, who have been very, very helpful on this project. Colonel Jill Sloan at the US Air Force Academy, and Eric Hunstein, a student currently at Virginia Tech pursuing his master's degree, formerly a Lafayette College student, as well as Luke Sokolowski, who is a cadet at the US Air Force Academy. All three of these individuals, in addition to Elise, have been very crucial in the development of GeoGrid Bridge 3, which is the focus of our talk today. Dr. Jim Collin has been an excellent technical advisor on this project, given his lengthy experience designing column-supported embankments. And finally, I'd like to again acknowledge the support of the Geosynthetics Technical Committee of the GeoInstitute. All right, just brief overview of where we're going today. So I've got it kind of in a pie chart here. We're going to start with a bit of intro. Going to go through a number of sketches and just to make sure we have a common set of terminology this afternoon. I'm going to talk a little bit about the overview of the low displacement compatibility method of design and the spreadsheet tool that implements that design method. Then I'm going to dive into a bit of discussion of the mechanics of the primary vertical load transfer mechanisms that are in play in column-supported embankments. Then I'm going to hand it over to Elise, who's going to guide you through a tour of the new spreadsheet in the context of a simple example. And then at the end, we'll wrap up and we can do some Q&A. Okay. So the assumption today is that we have some common familiarity with column-supported embankments. There's probably to varying degrees, but these are systems that are primarily used in transportation infrastructure, though not always. And this sketch shown on this slide is not my own. It's something I'm borrowing, but I think it does a good job of showing typical applications of column-supported embankments, where we're trying to construct over soft ground. We have concerns about large settlements. Perhaps we have concerns about stability. And so this technique bypasses these weak and soft soils using an array of stiff and strong column elements that carry a large portion of the new embankment loads. These systems are augmented usually by one or more layers of high-strength geosynthetics, and we'll talk a little bit more about that. All right, here's a very kind of simple sketch showing a typical profile for a column-supported embankment. And so the embankment is shown here in this two-tone color. The separate colors are used to distinguish the more kind of general structural fill of the embankment from a special layer near the bottom. It's typically between 2 and 4 feet thick. And that special layer is known as the load transfer platform or the load transfer mat. It's in this special zone of fill, which is usually a much more select type of fill. It could be a crushed stone or a very good quality sand. It's within this zone where the geosynthetic reinforcement is located. I've got just one little dashed line in this sketch representing the geosynthetic, but often multiple layers of geosynthetic are deployed through this LTP. Typically, these geosynthetics are geogrids. They can be biaxial grids or multiple layers of uniaxial grid offset by 90 degrees, or in some cases, a high-strength geotextile fabric is used. The gray shapes shown in this sketch are signifying the columns, and in this case, I've also shown some pile caps, which are sometimes, not always, placed on top of the columns. And so it's these columns which are attracting this new embankment load, which may include a live traffic surcharge. In terms of the stratigraphy below the embankment, more often than not, we have some thickness of a competent upper layer. And so this might be due to an existing sand layer naturally occurring. It could be due to a desiccated crust of the clay. It could be that there's some existing fill that's already on the site, or it could be that there's, in the pre-construction condition, there was no competent material and a granular working platform needed to be built in order to install the columns and ultimately construct the embankment. So more often than not, we have several feet of good material overlying the troublesome material. And using this low displacement compatibility design method we'll talk about, that presence of that better material comes into play and actually enhances load transfer. All right, typically our columns are installed through the soft, weak soil and into some sort of bearing layer. It could be a stiffer clay, or it could be to a dense sand or even rock. All right, I've got one slide here on the construction of column-supported embankments. The columns that are used are quite flexible in terms of what technology. In terms of the columns, we could use driven piles, although increasingly various forms of formed-in-place columns are used. So I've got a photo here showing installation of continuous flight auger columns. I've got a photo showing a bore displacement column, a tool for installing bore displacement columns. And these photos are courtesy of Jim Collin. I've also have a photo here showing construction of pile caps on top of the columns. So if we want to increase the area of support provided to the embankment by the columns, rather than enlarge the entire column, we can place a pile cap. And that has been used to good effect on a number of projects in the US. All right, so we're going to talk a bit today about the various mechanisms of vertical load transfer in column-supported embankments. But just to give you an overview now, we've got arching, soil arching that occurs within the embankment, including the LTP. If geosynthetic reinforcement is installed in the LTP, the tension that develops in that reinforcement transfers some vertical load into the columns. And also, we have another very significant mechanism of vertical load transfer within the subsoil, and that is due to negative skin friction between the subsoil and the columns as the subsoil settles down relative to the columns. And so this mechanism of load transfer would occur down to the neutral plane. And it is critical to know that all of these load transfer mechanisms require differential settlement between the tops of the columns and the subsoil between the columns. And so that's one of the hallmarks of the load displacement compatibility method, is that we consider that these mechanisms require this differential settlement for mobilization. All right, here's a definition sketch. We're looking down in plan view, and I'm showing different types of arrays that we can use for our columns. So on the left, you see a square array of columns. And in this case, I'm showing round columns. I could show instead square columns if we were using driven piles or using square pile caps, but I'm choosing to show round columns here. For our square and rectangular arrays, the key things you want to know are the center-to-center spacings of these columns, S1 and S2. If we're talking about a square array, these are going to be the same. If it's rectangular, they're going to be different. You want to know the dimension of the column or pile cap. And from these parameters, we can define a unit cell, which I have shown here in this dashed square. And the unit cell is the tributary volume for any column. And so looking at plan view, it appears as a square for the, in this particular instance. I can talk about this, the same things in terms of a triangular array. In a triangular array, we have also two potentially different column spacings in different directions, S1 and S2. And we have, again, the column diameter or cap diameter. And with those parameters, we can define our unit cell. Okay. Now, what's relevant today is that different locations within the unit cell receive different amounts of vertical support from the columns. So if we're looking at locations in the unit cell, and just for discussion, let's say we're talking about within the embankment. So the column is below us. These settlements in the soil above the column are going to be lower than anywhere else in the unit cell because those areas are receiving the most support from the column. Conversely, a location out at the edge of the unit cell receives the least support from the column. And so it is going to have, it is expected to experience the largest settlement within the unit cell. So if we're thinking about differential settlement, if we agree that the minimum settlement is going to occur over the column and the maximum settlement is going to occur away from the column, then we can define our maximum differential settlement. And for now, let's think about this differential settlement occurring at the top of the embankment, at the surface. And so from a design standpoint, for the purposes of providing good ride quality, we don't want the surface of our embankment to experience a significant differential settlement. Or else we could get a situation like this, right? Where this is a case history from the Carolinas back in the early to mid 2000s, where the embankment was too thin and differential settlements that occur at the base of the embankment, which we expect, were reflected at the surface of the embankment, which is not something we want. And to avoid that, we want to make sure our embankment is thick enough to be what is called above the critical height. And one way of estimating the critical height is provided here. All right, back to our sketch of the unit cells. Now let's talk about at the base of the embankment. So right now, we're talking about right at the top of our column and pile cap elevation. Again, our settlement at that location is going to be the lowest in the unit cell, and our settlement of the subsoil is going to be the highest in the unit cell. And so this is our maximum differential settlement at the base of the embankment. And this is the differential settlement that we expect and need in order to have these vertical load transfer mechanisms mobilized. And so it's this maximum differential base settlement, which is sort of the settlement that's our anchor in load displacement compatibility design that kind of ties together all of these load transfer mechanisms. Okay, so all load transfer mechanisms simultaneously consider this value of DSBD that is calculated. All right, so now that we've talked about sort of in the big picture these vertical load transfer mechanisms, we can think about how these mechanisms affect the vertical stresses throughout our profile. And so this is a schematic showing how vertical stresses are distributed, acting on either the column or the subsoil, the soil between the columns. So starting from the top, if we have an embankment of a particular height and a particular unit weight, and we've got some live traffic surcharge, in the absence of any vertical load transfer mechanism, we would all agree that that would produce a change in vertical stress equal to this value of sigma average. Okay, so then as we get mobilization of arching due to some differential settlement, that arching is going to transfer some of that stress through shear, given that some of the embankment material is going to be moving relative to other embankment material. We're going to get vertical stress concentration over the tops of the columns, okay, and we're going to use this terminology for that stress, and some vertical stress reduction over the soil between the columns. And so we can represent this load transfer in a dimensionless way using what is known as the stress reduction ratio. And if we're talking about the stress reduction ratio due to arching, we'll use SRR with this subscript EMB. Okay, and that's going to be the ratio of the vertical stress acting on the soil divided by what the vertical stress would be in the absence of any vertical load transfer. All right, now looking at the effect of our reinforcement. As that reinforcement deflects, develops strain and tension, we're going to get further load and thus stress concentration over our columns and further stress reduction over our soil. So this value is going to be higher than this stress over the column above the reinforcement. And so we need to define another stress reduction ratio to account for the effect of the tension that has developed in the reinforcement. So we'll call that SRR foundation. And it's this stress, this sigma soil geo bottom, which is the new stress felt by the subsoil that produces settlement. Okay, so the lower we can make this, the lower the stress is, it's the lower the settlements we expect. All right, if we just zero in on the contribution of the geosynthetic reinforcement, we can calculate a third value for the stress reduction ratio just due to the presence of that geosynthetic reinforcement. And so that we can calculate by taking the difference between the stress on the soil above the reinforcement and below the reinforcement, and then divide that by that average stress that we would expect in the absence of load transfer. All right, so that's the kind of basic terminology that we need in order to move forward this afternoon. So comp-supported embankment design is fairly complicated, involves lots of design checks. Among all the design considerations, two that we're going to talk about today are making sure that we have acceptable total and differential surface settlements. Okay, I mentioned earlier that we usually want to try to minimize the surface differential settlements as much as practically possible. We also want to make sure that our strain and tension that we expect in the reinforcement is acceptable over the service life of the embankment. So there's several ways we can go about answering these questions, and kind of the earliest design guidance that goes back to European practice with comp-supported embankments are these so-called two-step analytical procedures. And there's a number of them out there in the literature. What's relevant now is just to say that these two-step procedures, by their name, decouple the analysis of what kind of load transfer we expect to get out of arching and the load transfer we expect to get out of the geosynthetic reinforcement. Often, these methods do not satisfy vertical equilibrium, and these methods often do not consider stress-strain compatibility in the reinforcement, meaning that the tension in the reinforcement is not related to the strain in the reinforcement by some value of tensile stiffness. All right, the second type of design approach we can use is numerical modeling. And this is a true three-dimensional problem. So a true three-dimensional model is not going to need to make many simplifications. But there are still many models out there, and there's still much utility in using simpler numerical models. We can use an axisymmetric approximation of our unit cell, or we can model our embankment cross-section in plane strain. But in that case, we need to recognize that in plane strain, our columns are now continuous panels in and out of the screen. And so there's guidance in the literature on how to size those panels or assign properties to those panels to sort of adjust for the fact that we're representing a very three-dimensional problem in plane strain. The focus today, though, is talking about load displacement compatibility. So this is an analytical method. It doesn't require a numerical model, but it does require consideration of all these load transfer mechanisms in a coupled fashion, satisfying vertical equilibrium and considering stress-strain compatibility. And as Elise will go into detail on later today, we need a spreadsheet tool to be able to simultaneously solve these equations of equilibrium. Right, so the details of load displacement compatibility are captured in several journal and conference publications, but the easiest way to get access to the details of the methods are in GEC 13, and that's volume 2, chapter 6 is where you'd find information on LDC, as well as geotech tools, which I hope you're all familiar with. And this is a website that is accessible through the Geo Institute webpage, and no cost. You just create a login, you jump in there, and you can find information on all sorts of ground improvement technologies. And the list is expanding at all time, and there's a nice section about comp-supported embankments in there. All right, so as I've already said, we need a tool to be able to simultaneously solve these equations of equilibrium. GeoGrid Bridge, or shorthand GGB, is the tool to do this. There's a bit of history with this spreadsheet. So the original version of this goes back to the early to mid 2000s. So this was efforts led by Dr. George Fills and Miriam Smith. They were working with the Virginia Transportation Research Council and produced a manual back in 2006. The first version of that spreadsheet soon followed. And it wasn't until 2014 that Colonel Joel Sloan, a PhD student at the time at Virginia Tech, led an effort to update this spreadsheet with additional features. And this current effort, GGB3, is the first full from the clean sheet redesign of this design tool. And so because we were starting with a clean sheet, we were able to really sort of pick what capabilities we wanted to offer users and try to make the spreadsheet as modern as it can be. So off to the right here, there's a table that I'm not going to get into all the details on, kind of comparing the features for each generation of GeoGrid Bridge. But I am highlighting here some of the key innovations in the new version. So we've designed this new version to provide users more flexibility in the way that they can define the subsurface stratigraphy and assign properties, relevant soil properties. We've also added more flexibility in terms of how arching is modeled, in terms of how it mobilizes with differential settlement. And as Elise will go through, we've added a really nice ability to perform batch analyses with the new spreadsheet. And so you can use those in a probabilistic framework to calculate, to estimate the probability that the settlement may exceed some acceptable value. All right. So at this point, I'm going to just do a slight deeper dive into each of these mechanisms of vertical load transfer. And so the first one I'm going to talk about is arching. All right, and I'm going to be focusing on what is done within LDC. And so within LDC, the arching is considered using a version of Terzagh's arching theory that was presented for two-dimensional situations back in the 1940s. So this might be a situation where we've got a plane strain or approximately plane strain model where we've got a trap door here, say in the middle. And so if we have a soil tank and this trap door drops down, the soil not over the trap door is considered to remain stationary, while the soil over the trapdoor is assumed to move down uniformly. And we're going to get load transfer through shear as that moving soil moves relative to the stationary soil. And so this is a fairly well-established concept in soil mechanics. And so what I'm going to be talking about today is how we adapt this, or how people over the years have adapted this for the three-dimensional unit cell. Okay, so we're gonna get arching in the embankment below the critical height, because it's below the critical height where we have differential soil movement within the embankment, and that differential movement is essential for this shear transfer. All right, so I've got this graphic here to show this three-dimensional unit cell. Okay, in this case, I'm showing square columns. The dark brown is the subsoil. This lighter brown is the embankment. And I'm just showing that as one color for simplicity here. Again, our assumption for this model is that this soil overlying the column does not move, okay? And the soil between the columns moves down uniformly, okay? And for convenience, we're gonna find our unit cell centered on the middle of the soil rather than centered over the column. So it's the same unit cell, the same area, we're just shifting where it is centered. All right, so with this little sketch, let's define a little vertical increment okay, within this embankment height here. And this little increment has a thickness dz, okay? And as this little increment moves down relative to the soil that is assumed to remain stationary, the horizontal stress between these soil masses is going to, and in the movement, is going to develop shear stresses. And it's those shear stresses that are going to transfer load from the moving soil to the stationary soil, and then ultimately to the columns. So to model this, or to represent this mathematically, we want to look at how the vertical effect of stress in this increment changes over this incremental thickness. And so the self-weight of that increment, that is going to be influenced by the effective unit weight of the increment. That's going to cause the vertical effective stress over that incremental thickness to go up. Whereas the shear stress that develops between the increment, the portion of the increment that moves down and the portion of the increment that stays fixed, that's going to act to decrease the vertical effective stress. Okay, so and so the higher we make our unit weight, the more there's a tendency to have the vertical stress go up, but the more of an interface, the higher our interface shear strength, the more vertical stress we can shed through shear. And so we want to define our shear strength parameters, phi and c. Often for granular materials, we're not taking a non-zero value of c. We also want to know what our value of the earth pressure coefficient, which would, when multiplied by the vertical effective stress, is going to give us our horizontal effective stress at that interface. Published guidance, and what we recommend in the absence of better information, is to use a K value of 0.75. All right, and so this is kind of the understanding for a single increment, and you can imagine that we would have a whole bunch of these increments going down, and we can look at how the vertical stress changes as we go down through the embankment. All right, one simple way of kind of getting this concept in your mind, I found some dominoes in my house, and so I took 2 dominoes and put them between my hand, and I was able to suspend 4 dominoes above the ground, okay, just by the interface shear between the fixed dominoes and these dominoes that, in the absence of that shear resistance, would fall to the ground. Okay, so again, it's a similar problem, but again, something tangible here. All right. So this adapted Terzaghi procedure is implemented in all versions of GeoGrid Bridge. The first 2 versions use integrated forms of that differential equation, whereas the 3rd version uses that incremental form. And so this, by discretizing the entire embankment into these little increments, that is how we can provide more flexibility in defining more complex stratigraphy within the embankment. And so provided that you're using a thin enough value of dz, and usually a value of 0.1 feet or thinner is sufficient, the answer you get out of the incremental form is going to match what you would get out of an integrated form. All right. Thinking about how this arching is mobilized. Okay, so the arching is mobilized because we have this differential settlement at the base. And I've already introduced this concept of the stress reduction ratio, where if we have no load transfer, that value is 1. And if we had all of the new embankment load transferred to the columns, that stress reduction ratio would reach its other limiting value of 0. And so there's lots in the literature about how this arching might be mobilized with more differential settlement. The first form that I'm going to talk about is what's known as the bilinear adapted Terzaghi. This is what has been used in GeoGrid Bridge up to date. And it is as the name implies, a bilinear relationship with a linear ramp up from no arching to a full state of arching according to adaptive Terzaghi theory, and then holding at that fully mobilized state thereafter. This slope of the portion where we're ramping up and mobilizing arching, that piece is estimated using simple elastic theory. And for most conditions, we're looking at a differential settlement at the base. It's about 0.5 to 2% of the column or cap diameter. All right, another way we can look at the mobilization of arching, and I should back up and say that all of these three models that are shown on this sketch can be implemented in the new version of GeoGrid Bridge 3. The black line that's not highlighted right now, the solid line, that's the ground reaction curve that has been proposed by Daniel King and his co-authors. And this curve in its kind of full form requires defining several points in this relationship between stress reduction ratio and differential settlement. More recently, Dr. Jihan at the University of Kansas has proposed this simplified ground reaction curve, which requires definition of fewer points along this relationship. And so I'm highlighting that now because it's a little easier to talk about. It's also the subject of a paper that I'll be presenting at Geo Congress in Charlotte this spring. So in this instance, we're looking at mobilization of arching to a peak arching condition, which is estimated using application of other arching theories, such as the concentric arching model proposed by Suzanne Van Eckelen and others, as well as the Hewlett and Randolph method, which goes way back to the beginnings of column-supported embankments. So that would give us this point, and then there's a transition to the extent of arching modeled by the adaptive Terzaghi procedure, which many experts will say is representative of the type of arching you get at large strain, where we have a fair amount of differential settlement between the soil over the columns and the soil between the columns. All right, second load transfer mechanism that we want to focus on today is the development of tension in the reinforcement. And so I hope that all of you have had a chance to jump on a trampoline at some point in your life. And if you can think back to that experience and you're standing on the trampoline, you're suspended above the ground because of the tension that develops in that membrane, in that trampoline membrane. And it's the vertical component of that tension, which is satisfying vertical equilibrium. So rather than looking at the frame of our trampoline, we've got columns as our frame and geosynthetic reinforcement as our trampoline. Okay, and rather than this kid, what's acting down on our reinforcement is the stress acting over the soil above the reinforcement that I defined earlier. All right, so again, I'm showing this with square and rectangular arrays, and as well as a triangular array. This time I have square columns or caps shown, and it's appropriate this time to highlight that we can convert between round shapes and equivalent square shapes using an equal area relationship between those dimensions. And it's necessary to use a square column or cap shape when applying this analytical model, because the span distance between columns is important in the model, and that span distance is fixed for a square shape where it wouldn't be fixed for a round shape, okay, because of the circumference. All right, so as we move forward here, we need to recognize that it's the reinforcement across each of these spans, which is collecting the vertical load carried by the reinforcement within the tributary area for each span. So on this, focusing on this left-hand figure, this C1 span and this C2 span are the same because I've drawn these as a square arrangement. If this were a rectangular arrangement, these spans would be different because the spacing S2 would be different. For a triangular array, we also have two spans that ultimately transfer vertical load to the columns. And that's at C1 across this S1 center to center spacing, and C2, which requires using both S2 and S1 to determine. And it's within these strips where the strain and tension in the reinforcement will be highest. Okay, so as we go through this, we're going to be using what's known as the parabolic method to evaluate the tension and strain produced in the reinforcement due to this net vertical stress carried by the reinforcement. And so it is the total load carried by the reinforcement is going to be equal to this net vertical stress multiplied over the area on which that stress acts, which is the portion of the unit cell that's not supported directly by the columns. And that total amount of load is going to be distributed between the C1 span and the C2 span. And so one of the questions as we go through this model is how that load is distributed between these two spans. For triangular arrays, we use the fact that these spans cross at the center point here. So we know that the maximum sag of that reinforcement due to that load is going to be, those maximum sags are going to be the same. So we use that as sort of our anchor point in figuring out the load distribution between these two spans. We assume that the shape of this deformed reinforcement can be described by a parabola, and that allows us to decouple any tension that develops in that reinforcement into its vertical and horizontal components. And it's that vertical component which again is doing the vertical load transfer. Other things we need to know, we need to know and be able to evaluate the long-term tensile stiffness in our reinforcement. There's guidance on how to do that in GEC 13. And we also take advantage of an approximation within the parabolic method between the maximum deflection across any span and the strain, the average strain that develops in the reinforcement across that span. All right, so armed with that information, applying a little bit of algebra, we get a nice closed formed relationship between this maximum differential base settlement and the net vertical stress carried by this reinforcement and transferred to the columns. All right, similar thing for square and rectangular column arrangements. Now in this case, our spans don't cross at a common midpoint. So our maximum sags aren't required to be the same. And so to get to a closed form solution, we make an assumption that the load, this total vertical load, is distributed across these spans according to the percentage of the tributary area relative to the overall area and the unit soil that's not directly supported by the columns. Once we make that assumption, the rest of the concept is exactly the same as for the triangular arrangement. And we end up with this lovely equation that again is closed form that relates the maximum differential settlement at the base to the net vertical stress carried by the reinforcement. All right, so that's the parabolic method for evaluating the tension and strain in the reinforcement. All right, last load transfer mechanism. This is, we're going to both look at the compression of the subsoil and the load transfer due to negative skin friction or drag force. All right, so within the embankment, load displacement compatibility assumes that these embankment materials are adequately compacted such that the compression of the embankment material itself is insignificant. That said, the fact that there's differential settlement between the columns, this moves down, there's going to be a compliant settlement at the surface of the embankment due to that differential base settlement. Now, if we're above the critical height, that settlement at the embankment surface is going to be uniform. And so within LDC, we use the model by Russell et al. from way back in 2003 to estimate what that uniform surface settlement is relative to the column top for some value of maximum differential base settlement. And in this equation, lowercase a sub s is the area replacement ratio. which is the percentage of the unit cell area that is occupied by a column or pile cap. All right. Now focusing on sand soil. So within GeoGrid Bridge 3, soils are defined either or described as either being sands or clays. So if you define a soil as being a sand, compression will be handled using an elastic, simple one-dimensional elastic model, where the strain in that sand is a function of the change in vertical effective stress felt. The modulus, the Young's modulus has been specified for that material, as well as its Poisson's ratio. Similar model is used for the columns. We assume that the columns are also compressing elastically. We're going to have, most often than not, we'll have a different and higher value of Young's modulus for the column material, and as well as a different Poisson's ratio. And we can calculate the strain in the column due to some change in the vertical stress in the column. All right. The compression of the clay soils is handled using kind of the most complex analytical model, but it's one that we're all familiar with. When we do one-dimensional consolidation calculations, we use a nonlinear equation to get the one-dimensional vertical strain in that clay due to changes in stress. So GGB3 uses a traditional one-dimensional strain equation, just like we use in consolidation analyses. And so that means we can define pre-consolidation stress, we define the compression and recompression ratios, and handle things in the usual way. All right. Within GGB3, we can do time rate of consolidation calculations, and we do that using the method by Yanbu from 1965, which is an adaptation of Terzaghyi's time rate of consolidation theory to account for the fact that our ultimate strains are often not uniform. And particularly in this case, where we have negative skin friction, our strain distribution in the clay is expected to be non-uniform. And so this Yanbu method provides a simple way of handling that. Other than that, you're defining as the user parameters that you should be comfortable with, the maximum vertical drainage path length, and the coefficient of consolidation due to vertical drainage. Now, GGB3 does the settlement calculation down to the neutral plane within the profile. And so if you as the user are interested in the total settlement, not relative to the column top, but absolute, then you also want to calculate the settlement below the neutral plane. And this analysis is done external to the spreadsheet, but there are well-established methods that you can refer to in, for example, the driven pile manual is one source where you can read about the equivalent footing approach to estimating settlement. So we would just put an equivalent footing at the neutral plane and assume that those stresses are shed at 2 to 1. And so if you want to know the absolute, you want to know the total settlement at the embankment surface, not just relative to the column top, you take the settlement of the embankment relative to the column top, add in that elastic compression of the column itself, and add in that settlement below the neutral plane. All right, and the discussion about drag force is really simple at this point because we've already talked about it with the adaptive Terzaghi procedure. The mechanics are the same, where the differential equation is the same. In this case, we're looking at differential movement between the columns and the subsoil. And this value of K also accounts for any installation effects of the columns. So if we're using driven piles versus, say, a continuous flight auger pile column, then this value of K might be considered differently. And so I would encourage you to just use a static capacity analysis method that you're comfortable with to evaluate K for use in this model. All right, and there's our unit cell defined just in the same way as before. All right, so at this point, I'm going to turn things over to Elise, who's going to give you a tour of the spreadsheet in the context of an example.
All right, thank you, Professor McGuire. I'm going to give a brief example that's going to show you how GeoGrid Bridge 3 works and also sort of the user experience associated with it. So this is the example that I'm going to be taking you all through. It's a pretty simple embankment that's being supported by CFA piles. The embankment itself is 15 feet tall, is underlain by a 5-foot sand layer and a 35-foot clay layer. We're going to assume that the geosynthetic strain is limited to 5%, and both the total and the post-construction settlement at the top of the embankment is limited to 3 inches or 1/4 foot. So when you open the spreadsheet, this is what basically the landing page that you will see. And we're actually going to go ahead and open up the spreadsheet just so that you can see that in real time. And then we'll go ahead and go through the example on PowerPoint just for simplicity. Okay. So when you open up the spreadsheet, this is what you'll see. You might have noticed that you have to enable the macros, otherwise the spreadsheet won't work. Top left corner where you see the word simple worked example is where you're going to put in your most basic inputs. You're going to name the project, you're going to define your units, and it's really important to note that the units that you define have to be consistent throughout the entire spreadsheet. So you can use whatever unit system that you would like, but if you define feet, any length that you use throughout the entire setup has to be in feet, it can't be in inches or anything like that. Directly below those units is where you input the number of trials if you wish to run a batch analysis. We recommend using 1,000 trials. That's kind of the industry standard for a lot of other technologies that use a Monte Carlo simulation, but GeoGrid Bridge 3 has the capability of running up to 10,000 trials. If you just wish to use a deterministic analysis and not consider probability, you would input 1 into n, and that is actually the default value. Right below that is where you will define your post-construction profile. You'll give a name to each embankment layer, and you will define the type of layer that it is. The options are an embankment layer, a sand layer, and a clay layer. And if there are no layers that you wish to input, it'll be null. You'll notice that a lot of the cells have different colors and different text colors. So red text indicates that it is a user input. Black text indicates that it's something that is automatically generated by the spreadsheet. As well, the highlight color of the cell is important. If it's green, that means that the input that you put in as the user is acceptable. If it's yellow, it means that you can put an input in, but you don't have to put a value. And if it's red, that either means that a value is required and the cell is blank, or that the value that you put in is nonsensical and needs to be changed. So that makes it pretty easy to see exactly what you need to input as the user and what sorts of parameters are necessary for each type of soil layer. So you go ahead and for each layer define the thickness and each of the parameter values that you wish to use for that layer. And then after you do all that, you'll go ahead and define your surface loading conditions. That's pretty much all pre-prescribed, so it's pretty simple to do, but it allows you to input a preload for during construction, the surface loading that you expect post-construction, as well as the time available in between when you construct the embankment and when it is actually put into use and paved. You can also define the arching model. We talked about the different methods of arching that are capable in GeoGrid Bridge 3. So right now it's set to the bilinear adapted Terzaghi method, and you'll also have to put in the relative soil parameters for the arching method that you select. Directly to the right of that is where you'll input the column geometry. You'll input the shape and the size of the caps and the columns, and you'll also define the array type. And if you scroll down just below where you'll input the array information, you'll find where you'll put in information regarding the stiffness of the geosynthetic reinforcement. And those are all of the inputs that are required for you to run a deterministic analysis of GeoGrid Ridge 3. So after you do that, you'll scroll up to the top of the spreadsheet and press the Solve GeoGrid Ridge 3 button. And after you do that, it'll spit out those blue numbers that you see in the output section. Blue indicates that it is a result from the GeoGrid Ridge 3 analysis. And if you choose to run a batch analysis, you will also see a probability of exceedance for the limits that the user defines for the spreadsheet. So that's pretty much what the spreadsheet looks like. We're going to go back into PowerPoint at this point and walk you through an example. Again, this is the color scheme, but the first thing that you'll do is you'll develop the post-construction profile, and that's located again in this corner. So for this example, we have the 15-foot embankment. We'll separate that into the general embankment layer and the load transfer platform and define the thicknesses for those. An important note is that if a layer is bisected by a water table, you need to separate it into the layer above and below the water table. So you'll see that we did that for the sand layer here. And then lastly, we'll input the clay layer. And if that's the last layer, you don't need to put in anything else. Next, we'll put in the material properties for each layer. We'll go layer by layer for this in the example. So for the general embankment, anything that it is an embankment layer only requires a unit weight, a earth pressure coefficient, and the friction angle. So we'll go ahead and use those values and put them directly into the spreadsheet. Again, it lights up if you need to put something there. And so it's very simple for the user to know where they need to put different parameter values. Same goes for the sand subsoil. Again, we need to break it up into the sand above and below the water table. And there are a few extra parameters that are required, including the Young's modulus and the Poisson's ratio. Again, you will calculate the earth pressure coefficient using a static capacity analysis. We use the beta method in this example. And you'll go ahead and put those inputs in where they are required. Lastly, you'll do the same thing for the clay subsoil. Clays are going to require the most parameter inputs, but a lot of them are similar to the sand and embankment layers as well. Main differences are that you need an OCR as well as a compression ratio and a recompression ratio for the clay layer. You'll also need to define the strain profile. We chose a linear profile in this example, and also the maximum drainage path. Because we are assuming that this example is doubly drained, the maximum drainage path is going to be the total width or total depth of the layer divided by 2. So after you input all of those parameter values, you'll go ahead and define your loading conditions. For this example, there is no preload that was prescribed, so we'll just enter 0 for that value. 250 is the traffic load that we are expecting, and there will be 60 days available for consolidation before paving and traffic load is applied. So we'll just go ahead and enter those values directly into the spreadsheet. Next, you'll input the column geometry. For this example, no pile caps were specified, so we'll just say none there. The columns are 2-foot diameter concrete columns, so we'll put in that they are round as well as the diameter, and we'll put in the relevant properties of those columns, which include the Young's modulus and the Poisson's ratio. Additionally, the array is square. This is a drop down again, so the options are triangular or rectangular, so you'll put in rectangular, as well as the center to center column spacings. Then you'll put in the reinforcement stiffness. For this example, there are 3 layers of biaxial geosynthetic installed in the load transfer platform, and each layer has a long-term stiffness of 24,000 pounds per foot. So you'll go ahead and multiply 24,000 pounds per foot times the 3 layers, and you'll get a total stiffness of the geosynthetic of 72,000 pounds per foot in both axes. And lastly, you'll specify the mobilization of arching model. Again, the arching model selection is a dropdown, so you have the option of BAT or the simplified ground reaction curves. For this example, we selected the BAT model and input the relevant modulus of arching soil, as well as the relevant Poisson's ratio. And after that, you are done inputting anything into GeoGrid Ridge 3. So you'll go ahead and click the Solve GeoGrid Ridge 3 button in the corner. For this example, on my machine, it took about 5 seconds to run, which is a significant time improvement relative to previous versions. It, of course, will vary based on the computer that you're running it on, as well as the complexity of the example that you're running. But we found that 5 to 10 seconds seems to be pretty consistent for this type of model. In the outputs, you'll see that the strain in the geosynthetic is below 5%, which is good. Total height is greater than the critical height, which means we're not going to get that differential settlement at the embankment surface, which is also good. And the settlement for both the total and the post-construction settlement is below that limit of 3 inches or 0.25 feet. It's important note to remember that the user has to run separate analyses for failure mechanisms that aren't considered by the LDC method, such as lateral spreading and global stability, as well as column capacity. So you could be done there, but you could also run a probabilistic analysis, which is something that I'll talk about in a few slides. This is one of the graphs that is automatically generated in GeoGrid Ridge 3 that I think does a really good job of showing how the load is distributed through the different mechanisms. So this first section where you see O is the load, the percentage basically of the total load that is transferred directly through overburden. Next, you'll see that arching plays a pretty big role in the load transfer mechanism here. And the reinforcement plays a smaller but still pretty significant role in transferring the load. The downdrag or the negative skin friction also plays a very significant role, and you'll see that that varies with depth until you reach the neutral plane. And before the neutral plane, you'll see that the subsoil itself is also taking a portion of that load. And no matter what the depth, the combination of all of these load transfer mechanisms will equal the weight of the embankment and the surcharge. So if you wish to run a probabilistic analysis, that is something that we're pretty excited about because it's a new capability that we have. In this example, we're going to run 1,000 trials. That is, again, the number of trials that we recommend. And we're going to assume that the serviceability limits are the same that we mentioned previously. The reason that this is important is because we know that soil parameters have a lot of variability and that there's a lot of uncertainty associated with them. So it's important to see how slight changes in that variability will affect the overall design results. So for this example, we're going to consider uncertainty in the unit weight, the earth pressure coefficient, the friction angle, the compression ratio, and the recompression ratio. We're going to assume a normal distribution for each of those parameters. GeoGrid Ridge 3 allows for either a normal or a log normal distribution. And we're going to assume that there is no covariance between these parameters. Currently, GeoGrid Ridge 3 doesn't have a capability of considering covariance, something that we're considering adding, but as of right now, we assume that there is no covariance between parameters. So the input for the Monte Carlo simulation is actually directly to the right of where all of the deterministic analysis inputs are. And you'll see that it will use the average value of each parameter as the value that you input in the previous example. It'll allow you to prescribe a distribution based on the soil layer. And it requires a standard deviation as well as an upper and lower bound. So I'm only going to show you the unit weight, but the process is the same for all of these different parameters. We're going to assume a coefficient five for the layers below the water table. And then we're going to define the standard deviation as the average value times that coefficient of variance. So 0.03 times 130 is going to give you 3.9, etc. The upper and lower bounds are defined in this example by the 3